Hello, my name is John Barnes. I'm the Technical Manager at Enginesoft UK. This is a webinar, part of a webinar series on modeFRONTIER. We're going to be looking at some of the analytic tools and help you to explore your design space with specific attention today, looking at the sensitivities and local effects in your design space. What I'd like to take you through is just a few things. I'll just give you a brief introduction to modeFRONTIER, introduce a little case study, hopefully that'll be very short, but then spend a bit of time, 15 minutes, just demonstrating some of these tools in modeFRONTIER for exploring your design space, and then there'll be some opportunity to ask any questions, some text questions, so end. So just to get you up to speed, modeFRONTIER, it's a multidisciplinary optimization tool. Typically when you're designing something, you've got some targets, maybe you've got a number of set of disciplines that you're looking at, and we might analyze that and have some baseline value. If we were doing something a little bit more smart, we might want to do some optimization, maybe a single discipline optimization, but typically if you're looking at one of those disciplines, it comes at the detriment of other disciplines. But when we're looking at MDO, we're trying to push all of our disciplines and try and get a balance between them and try and optimize them in all directions. Now, some of the key things to be able to achieve this is integration, automation, and exploration. Now, we're not going to be looking at necessarily the integration part or the automation part today, but once you've done that, can you then understand your data? So we'll be looking today at a little bit of the exploration side. modeFRONTIER itself is a workflow-based tool for integration. You can build some very simple workflows, get things running quite quickly, but where you're an advanced user, we can map out quite large, complex, multidisciplinary scenarios and define some very complex problems. modeFRONTIER itself integrates with many tools, whether you're connecting to some CAD tools or some CAE analysis, whether you're trying to run things over the network or connect with databases, if you're trying to run some mathematical operations using Excel or MATLAB or some Scilab or scripting tools, operating with files, reading and writing from files, running a range of scripts, defining some logical statements to rerun different parts of your workflow based on different conditions, or if you're indeed actually trying to integrate and optimize with itself and define some very sophisticated logic. So all those things are possible, but this is the area that we're going to be looking at today, is once you've been able to integrate and automate a whole CAE process, you can generate a whole load of data, but can you really extract the benefit from that, that data set? So rather than running designs one at a time, once you're running thousands of designs at a time, you're really looking at typically multi-dimensional space. You have many input variables, many responses. How do we understand how that data relates? First of all, can you visualize the design space using a response space, as you can see in the top right-hand corner? Can we train these surrogate models, response surfaces? Could we do any statistical analysis and work out which variables relate strongly to others? And in this diagram down in the bottom right-hand corner, how can you understand what goes in at one end will come out at the other? Can we make those decisions with an objective way, rather than making subjective decisions that might be based on some experience or some discussion that we may have in-house in our organizations? So today we're going to be looking at a bike frame optimization, just for something to talk about and to talk around. This load case is a bike. There are two load cases, one where the cyclist is going downhill, one where they're climbing uphill. The difference obviously is that when you're riding, there's a force that's exerted on the seat and on the handlebars, but going downhill you typically won't be pedaling, so there'll be no force on the pedal. but when you're going uphill, you'll be putting in a harmonic force into the pedal. So we're going to be looking at those two load cases. There are going to be a number of inputs that we might want to change about the bike design, the length of some of the posts, maybe the Young's modulus, and the cross section of the tubing. In this case, we might want to be looking at the mass, looking at the static stress and the dynamic stress, looking at the yield and the fatigue as outputs. And then on those outputs, we might want to be applying certain objectives and constraints. In this case, this will be a multidisciplinary problem with a multi-objective problem with three objectives: one to minimize mass, one to minimize the maximum stress of load case 1 and of load case 2. And in addition, we want to apply some constraints to make sure that the static and dynamic stresses are below a particular safety limit as well. And we'll show you how those things are visualized inside modeFRONTIER. Now, this is the bit that's probably of more interest. That's just setting up and giving you a bit of background. I'll now flick to modeFRONTIER to show you how you would look at this problem. So this is the modeFRONTIER workflow. This is the integration and optimization part, so we won't dwell on this, just to note that we have a series of inputs, a series of outputs, and we're running it through a solver to generate those results and do those calculations. Now, this optimization has been done already, and we've already managed to generate a number of designs. So I'm going to go straight to show you some of the data that we have. And once modeFRONTIER has run, it will typically store that in a standard work table. I have 320 designs that have already ran. They have started from a particular sampling method called a uniform Latin hypercube, a way of sampling the design space, and then it's gone on and it's ran a number of generations using a genetic algorithm called MOGA2. And as it is ran, and we've got a series of new designs, each design has improved on the design before as we go down the list. What you will notice is that a number of the designs are in yellow. That simply means that these designs have failed the particular constraints. So we've applied constraints on the yield and the fatigue, and they have certain limits that they have to be greater than a certain value. And we can see where they have failed those constraints. Now, as you can see, that as the algorithm has progressed, fewer and fewer designs fail those constraints. So the algorithm is learning how to solve this problem. But the nice thing here is that we can see the list of our inputs, values, what has been tested, and then what their corresponding outputs are, and how they perform in terms of their objectives and their constraints. This is pretty much the kind of basic way in which we might want to look at that data. There are certain filtering that we can do, and tagging of categories. We can select data and apply and operate with that data, either rerun that data or put them into new tables or to manipulate them. But the most useful thing to be able to do is obviously to plot some charts and some graphs. And there's a wide range of different chart types that can be used to really do the data mining and do the design space exploration. We'll just take a few of them today. So if we look down here on the left-hand side, we can open up maybe a few charts that I've already got open. So one of them, the important ones, perhaps, is looking at a bubble chart in 4 dimensions. So here we are. We can look at our table. We can select different sets of data and then plot on the bubble chart different values. So if I was to look at 2 input values on my x and my y axis, my third axis, I could look at the mass, so the color of the bubbles. And also I could take another dimension and plot the shape of the bubble as well. So here we have a bubble chart. We can look at our two inputs. This is the radius of I believe, the yellow part of the frame and the red part of the frame, and we can see the corresponding mass. So the colours that are in red are the designs that have low mass, high mass, and then we can look at perhaps some of the static stresses in terms of the size of the bubble. So there's nice tools to be able to understand your design space and begin to look at it, but some of the real benefits is that all of these charts inside modeFRONTIER are connected together, and we can visualize them alongside each other, and any design that we select on one chart we can typically select on another chart. So if I was to select on the design table, I can then see it selected in an appropriate manner on another design table. I can also mark things so that they are also highlighted but in a slightly different color in terms of green as well. So there's another chart that I would like to show you, which is the parallel coordinates chart. And we'll try and link this one into the other set of charts. Here we'll look at all of our inputs and look at all of our objectives as well. And what this creates is this wonderful spaghetti-like chart. And this is really a great tool to be able to look into your designs and actually move around your design space and to begin to do a number of different what-if scenarios. So here we have a number of columns, one for each parameter or input parameter and our three important output parameters, and each line that runs from left to right is a particular design. So this design here I can see running from left to right, and it will also be highlighted on the other charts as well, so design 214. But the real power of this chart is the fact that we can use these filters to drag designs from top to bottom. So if I wanted to only look at designs that had a mass below 1.388, we could then trace back what that means in terms of the inputs that would create that region of the design space. And I could do a number of what-if scenarios. Maybe I want to look at the minimized mass, but maybe I would want to also look at the higher values of stress for whatever particular reason, and I could start doing a number of what-if scenarios. Now, to make this even more powerful, there is a synchronization tool that allows a much tighter integration or synchronization between this parallel coordinates chart and the other charts. So now if I wanted to filter out any designs with a Young's modulus below, maybe we're told by the designer that we can't achieve this material above a certain level and we want to do some sort of post-editing, we can then see how that happens on the rest of the charts, and it will physically filter out all of those designs on the other charts. So I can see exactly which designs make up this filtered set of results here and what they mean in terms of the design space. So if I was to minimize the mass, I could see in terms of my radius in both R yellow and R red, which areas of the design space we can achieve that in. Maybe if I was to then drag it right to the top, we would then notice that they're also in a completely different area of the design space. So we begin to get some spatial awareness of what the changes are in one chart and look at where we are in the design space of another chart. When we often go into engineering meetings, this is a powerful tool because often we're told that once we've found an optimal design, go back and rerun it because either that performance is good but the mass is not so good. So here, if people aren't happy with one particular design and the mass of the design, then maybe they could go and look at another design that is not so important. And because you've already explored the design space, you can happily go back and find another method. But here I just want to move on to some of the statistical tools. This is a data set that we've generated. Now we could go into looking at some of the correlations and work out what some of the interactions are between these variables. This can be typically done through a correlation matrix. But there are some important things about doing this analysis. What I have here are two correlation matrix charts of all of our input variables, and you'll notice that this one has telling me that I have correlations between my inputs, that if I'm changing the length of LB, it has some correlation to my Young's modulus. Now that I know in reality that that is not true, it doesn't matter how much I change the Young's modulus, it does not change the length. Now when we do this analysis, you can get these inaccurate correlations simply by the data set that you're running upon. So here I'm running this upon my design table. My design table is an optimization. If I was to look at my design table in 3D and I was to look at my three objectives in a 3D scatter plot, you'll notice that a lot of my designs are tightly populated around my Pareto front, which is this curve here. And it's not an even spread of designs over the data. When we do this kind of correlation analysis, we want to do it over a design space that is much more uniform and better sampled, and this is what is represented by this correlation matrix. And this has been done on a different table that has a much better sampling method. So if I was just to take a couple of the parameters from the design table and look at that spread of data, and to look at the spread of data on another design table, which is this one here. If I was to draw a regression line through this table and a regression line through this table, this is telling me that there's a strong correlation between LH and LB, and then this table is showing me there's very little correlation between, and all the difference is the way in which we've sampled the data. These are false correlations. I'm just going to go and open up another set of data from modeFRONTIER, which has a very uniform way of sampling the data set, and I then just want to show you some of the correlation charts that you can then look at using this data. So in this case, if I was to use this scatter matrix chart, I could look at my data in my design table. Again, I could look at all my inputs against all of my objectives. In this case, now that I know that there's zero correlation between my input variables, I can have strong confidence that when I look at the relationship between my outputs and my inputs, that they can be trusted. So here, these values are between -1 and 1. If there's a 0 value, there's 0 correlation. If there's 1, there's an absolute positive, and if there's a -1, there's absolute negative correlation. And the nice thing about this chart is not only does it give you a single value showing that my masses are heavily correlated to the thickness of the yellow frame, but I can also get it back to the scatter chart, and I can also look at some of the regression lines through that data, and I can start to look at the spread of the data that has been generated. Now, these are very traditional tools. These are just looking at the main effects, and requires quite good quality data to be able to do this analysis. Now there is this other tool called the sensitivity analysis tool inside modeFRONTIER, which is incredibly powerful. In the same way we can select our objectives and our input factors, but the same data is just being represented in a slightly different way. But the great thing about this is that we can use it not just on good quality data, but it works with poorer quality data as well. And it represents the correlations in this nice bar chart style. So in this case, I've managed to train the same data over my 3 outputs, and it lists the factors or the main effects in their order. So again, the thickness of the yellow comes out on top, But if I wanted to also look at some of the interaction effects, I can turn those on as well. So not only does it list the main effects, but it will also rank where the interaction is. So I know that the radius of the yellow part and the thickness of the yellow part, their contribution together, their interaction, is also quite high, but is ranked lower than the individual main effect of the thickness of yellow and the radius of yellow. So we can use this tool in a way that we can quite quickly assess the correlation between our variables. If we want to filter out some of them, we can ask it to only tell me what the top 4 main effects are, or if we wanted to look at effects that only make up 90% of data, or let's say 80% of our data contribution, then we can filter those out as well. So a very powerful tool, and this can be used in a number of ways. One way is to reduce the number of parameters that we're looking at in an optimization by screening them out. So if we know that a variable doesn't have an effect, then why look at it as a design option or design variable, and we can simplify a lot of our analysis. Also, this can help fill in any gaps in our knowledge. Quite often in our organizations we have disagreements about which parameters affect, and quite often most people understand the first 2 main effects of what's driving the system, but we often have a lot of discussion about the interaction effects and some of the lower or lesser effects in our system. And if we do this kind of analysis, then we can often draw a line under those kind of typical discussions and arguments. So I think that's all that I wanted to share with you today. There are many other tools inside modeFRONTIER to be able to delve into to understand deeper things about distribution analysis or multivariate analysis, but this is all for today, and if there are any questions, please ask me. Thank you.